the rational and the irrational. So largely we're thinking decimals. So the idea of a rational number is one of two things. If I give you a decimal that terminates, if I can get my pen to work, try this. Maybe not, let me get a new pen. If I get a decimal that terminates, so I was gonna write 2.5 there. So that's a decimal that just ends. So 2.5, 2.625. As long as the decimal comes to a stop, that is a rational number. Or it maybe doesn't end, but it repeats. So if I do 2.6 repeating, which I think we're all then familiar, we can, instead of having to write it with the sixes and the dots, if we draw our little repeating bar over the top of it, those are rational numbers, decimals that terminate or repeat. What are irrational numbers? The one that everybody knows is pi. You have seen that at some point in your life. And that is because that is a decimal that never, notice how it's not repeating, and it just goes on forever and ever and ever. It never terminates, and it does not repeat. That's the one that you're most familiar with. What we are dealing with now, I'm going to erase this guy. The other irrational numbers we get are when we do square roots of numbers that are not perfect squares. So if I ask you what the square root of 7 is, if you throw that into your calculator right now, that's going to give you a decimal that does not terminate and does not repeat. If I give you the square root of 11, 11 is not a perfect square. That's going to be an irrational number. The decimal doesn't end and it does not repeat. It just goes on and on forever with random numbers over and over and over again. So any of these radicals that we've been working with that we can't simplify in the end, those are irrational numbers, okay? All we're gonna do here is make sure we understand the difference between those two. So if you look at number 1, we have a square root, but this is one where we should be able to do both of these. If you remember yesterday, we said a square root of an entire fraction is really just the square root of the top and the bottom. So the square root of 25 is 5. The square root of 49 is 7. As long as we don't get one of these guys, a square root of a non-perfect square in our answer, then we are dealing with a rational number. All right. If I threw that into the calculator, it's going to give me a decimal, but it's going to terminate. When you now compare that to number 2, notice how that's a decimal. There's no pattern there that's repeating, just random 6, 2, 5, 3, 8. And then when you see these little dots behind it, that means we just continue on forever and ever and ever. So there's no repeating pattern. It never stops. That is the definition of an irrational number. The next one, you're going to do a couple of operations and then just see what that results in. Since these are both square roots, we can go ahead and multiply those together to get a 36. And then it just has to remain underneath that square root, since that's where the 3 and the 12 were originally. And then since that ends up being a nice perfect square of 6, that's a rational number. And the only time we get irrational is if it's a radical of a non-perfect square or a decimal that doesn't repeat or terminate. All right, so now number 4, here. The number in front of the first one is 2. The number in front of the second one is a 3. So those get multiplied together to give you a 6. And then the square root terms, the 5 and the 3 get multiplied together to give you a 15. And then that's the square root of 15. So then what you have to now ascertain or determine, is 15 a perfect square? Can I actually do the square root of 15? No. When that happens, that's when we're dealing with an irrational number. So this is irrational. Okay. Yeah, go ahead, Kim. You could try. Yeah, I mean, it is irrational, but the reason it's irrational, the only way I'm really going to get a 15 is with 3 and 5, right? So I can come up with two numbers that'll give me a 15, but is 3 or 5 a perfect square themselves? No. So just because of that, since we can't go any further, that's how we're going to know that this ends up being irrational, because we can't simplify that anymore. We end up with a square root of a non-perfect square. Okay. All right, now number 5, see this little repeating bar? Because this repeats, even though it doesn't ever end, as long as it repeats, we would still consider that to be a rational number. All right, number 6, we're going to do a -6 times, and then we actually know what the square root of 4 is. The square root of 4, we all know, is 2. So the value of that thing overall, when we simplify and multiply, is a -12, definitely a rational number. All right, let's do 7 and 8, see what we think before we move along here. All right, so number 7 is a decimal. So as soon as it's a decimal, you now have to determine, is that repeating? Does it terminate? As long as it repeats or terminates, then that's a rational number. So this doesn't repeat. There's no, 757575, but it does stop. It's just 9.75. There's no dot here. There's no dot saying this goes on forever. There's no bar over the top saying that that goes on forever. So that terminates, and any decimal that terminates is a rational number. Okay. And then number 8, we can go ahead and divide 16 and 2 to get an 8, but then it's the square root of 8. Can we, what do we think about the root 8 there? Okay, so this one we can break down with a 4 and a 2. So a root 4 times a root 2. We do then get a perfect square, as this is a 2 and then a root 2. So even though this 2 is good, don't we still end up with the square root of a number that's not a perfect square? Because of that, this is going to be an irrational number. All right, and that's kind of what we're dealing with now, is how do we handle irrational numbers, which are the square roots that are not perfect squares, okay? All right, last couple, or next set of problems. It's called the root method for solving a quadratic. We just did quadratic equations last chapter. Or cubics. Cubics just means we have powers of 3. So it says to solve quadratic equations or a cubic equation in the following form. So I'm going to have you write down this. So let's say we have x squared equals, let's do 4 in this case. Or if I give you an x cubed, because that's a cubic, we'll say that is equal to 8. So if I give it to you in that form, so one's a quadratic. Remember, quadratics have powers of 2. A cube, so a cubic graph has a power of 3. So that's all that's saying. The first thing we want to do, and in this case we've already got it, is isolate the variable term, or the cube, or let's do this. Isolate the squared term slash the cubed term. So we want to get it by itself, if at all possible. Once we've done that, what we want to do is we want to eliminate the exponent. So we either want to get rid of the square term or we want to get rid of that cube term. And we'll talk about how we're going to do that. And then after that, you're going to solve the equation that remains. So solve the resulting equation. All right. So we always want to get square term or the cube term by itself. The reason we want it by itself so that we can then get rid of the exponent. Once we've done that, you solve your equation like you have been for a number of years now, okay? So here's our steps. We want to isolate the squared term or the cube term. So in number 9, that's already done. This x squared is all by itself. So that's our first step. Then we want to get rid of the square term. So here's what I want you to actually do first. Before we actually solve this legitimately, just tell me what these answers are. Like, what could I square to get 25? Because whatever the answer to that question is your answer, right? Like, whatever squared equals 25 is your final answer. That we should all be able to do. All right, what do you get, Cam? Good, so 5? Okay, we all agree with Cam? Is there any disagreement or at all, or any supplementing that answer? No? I like the 5. 5 is good. What else? Anybody? Ahmed did? I didn't hear. What did you say, Ahmed? Good. Can't we also do a -5 squared and get a positive 25? So aren't there really 2 answers to this? All right. That there is where you need to be very, very careful, because this is where people are going to mess this up. So the way we're going to solve this, we're going to isolate the square term. That's already done. This guy's already over there by himself. What we then need to do is to get rid specifically of this squared. And you actually do this a little bit in Math 1. The way we get rid of a squared exponent is with a square root. Okay? So if I'm going to do that to the left-hand side, I better do the exact same thing to the right-hand side. So the square root, so kind of understand what's happening here. This square root cancels out the squared, and all we are left with is an x. And then that would equal, and then now understand, this is the biggest thing to keep straight so you don't mess these up, because this will be the thing that people miss. Whenever we do this square root, there's 2 different answers here, right? We had a positive answer and we had a negative answer of 5. Both the positive 5 and the negative 5 that gets squared, that's how we're going to get our 25. So whenever we do that square root, it produces two different answers, the positive solution and the negative solution, okay? This actually is the same exact thing as this. It's saying one answer is a positive 5, one answer is a negative 5, okay? So now, number 10. Now we do need to isolate this. So we want to, basically, what I have highlighted in yellow, we want to get that by itself. So all of your old algebra skills of solving an equation, if I want to isolate x squared, I'm going to subtract 5 first. So subtract 5 from both sides. The 2x squared is still here, and it now equals 18, as those cancel. We still don't have that squared term isolated yet. We now need to get rid of that too. So if I had 2x squared, just like again you would have done in solving regular equations, you now divide by 2. These will cancel, and we now have x squared equals 9. So what we've simply done is this first step. We've isolated that squared term. Once we have that isolated, we now want to get rid of the squared exponent, and the way we get rid of a square is with a square root. All right, so now as we do that, we are going to get a positive and a negative answer to this, because it doesn't 3 and -3 both work. -3 squared is 9 and a positive 3 squared. So the square root cancels out our x, and we now get a positive and a -3 as our final answer. All right. I want to give you one more of those before we jump to the number 11, because 11 is where people tend to really have some issues with these. So let me do a 10b up here. And let's do 3x squared plus 6. How can I get a nice number out of that? 3 plus I'm getting old. Mr. Kuwit's coming up with these off the top of my head. 300. All right, do 306. So 3x squared plus 6 equals 306. And see what we think. Is it my messy handwriting?
Yeah.
All right, so again, your first step, just try to get that x squared by itself, just like you would have been if there was no squared there when you were solving equations back in the day. And then we want to get rid of the square term. All right. So let's do kind of the first step, the first couple steps in terms of let's get this by itself. So in order to do that, we want to subtract the 6 over. So these would then cancel. We now just have a 3x squared on the left. And then that equals 300. The 3 then we want to get rid of. So we would divide by 3. So these will cancel. I'm going to move this over here. So now x squared is on the left. And then 300 divided by 3 should be 100. So just think in your head right now, shouldn't we get two answers, 10 and negative 10? 10 squared is 100, negative 10 squared is 100. So those are our two answers. The way we will get that when it's not quite that easy is you get rid of a square with a square root. So this now gives us an x, and then we have to understand whenever I do this radical, this square root, there's two different solutions, the positive solution and the negative solution. And in this problem, the square root of 100 is a 10. So we should get a positive 10 and a negative 10. So the big thing to take away of this, when I take this square root, that should give me both a positive and a negative answer to that square root. All right. With that now, these are the ones, please be careful of, that people tend to mess up. So number 11, notice now, isn't the square by itself? So the squared is that entire parentheses. That thing is already isolated. So, yeah, go ahead, Cam. Go ahead. Let me turn you up a little bit. I can't quite hear you. All right, go again. What's that?
What happens if the square root is not doing that?
Well, we'll get to those, yeah, because they're not always going to be these nice perfect squares. Yeah, there's many layers to this that will slowly peel off, but eventually we'll get to that, yeah. So be patient, Ahmed, and we'll get you there, okay?
Okay.
All right, so now number 11. This squared is already isolated. So this whole parentheses is your square term. So we've got step number 1 done. Step number 2 that we listed on the previous page is we get rid of the squared with a square root. So we are ready to take the square root of both sides right now. When I take a square root, it cancels out the squared. So the only thing that's now going to happen, we're pretty congested here, get rid of some of this. The only thing that's now going to happen is this square here is going to cancel out, or the square root and the square are going to cancel each other out. The only thing we would be left with then is the x minus a 4. On the other side, we don't just get 6, correct? Just like the previous 3 problems that we did, we should get both a positive 6 and a negative 6 when we take that square root of 36. There's 2 numbers I could have squared to get 36, the positive and the negative. All right. We now need to solve this equation. And it's weird. It looks a little bit different than anything you've solved before. And there's a couple different routes we can now take with this. And I don't know which one I'll settle on. You can kind of decide what you want to do. So one way, so let me kind of split this up. So one way is understanding that what this really means is I'm going to take x minus 4, and I'm going to set it first equal to the positive 6. And then I'm going to solve that. So just add 4 to both sides, and x is going to equal a 10. However, we also have to take the x minus a 4, and notice how this is a negative 6 also. That's what that little minus in front of the 6 means. So I'm also going to do x minus a 4 and set it equal to the negative 6. Don't think you're going to get a negative 10 here. We don't just get 10 negative 10. Don't be that kid when the time comes. All right, when I now solve this, you're going to add 4 to both sides, just like we did before. Our other answer should be a negative 2. Now, back when you would have first started solving linear equations, your teacher would have said you can always test these. So now let's take this value of 10 and let's plug it in up here. So if I did that, what is 10 minus a 4? Isn't that 6? And isn't 6 squared going to give you a 36? So that's correct. Let's test this negative 2. So same thing, take the x value of a negative 2, plug it in right here. So if I now do a negative 2 minus a 4, isn't that a negative 6 squared? Doesn't a negative 6 squared give you 36? Yes, so we know we are correct. Now, here's your other way to solve this. So I'm going to take the same exact equation, and then you can decide what you like the best. Either setting up 2 different ones like I did over here, or doing this. Let's just add 4 over to both sides right away. So what this would now give me is x equals a positive 6 and a negative 6 increased by 4. So we can write it that way. And then what you're simply going to do, think about what is a positive 6 plus 4. Isn't a positive 6 plus 4 going to give you not a 4? Sorry, a 10. So that's one of the answers that we got on the other side. You can also then do yellow, the negative 6 plus 4. Do a negative 6 plus 4, and doesn't that then give you the negative 2 that we got on the other side? Okay, so kind of up to you how you want to go about solving those. All right, so now let's see if we understood that. Try number 12. Oh, you know what? Gosh, I wish what happens when you share materials. Let's see here. Darn it. Let me do. Yeah, go ahead and let's do number 12. We'll go ahead and do number 12. Notice how that square term is already isolated. We have that done already. All right. So we're ready to get rid of the squared. And the way that we get rid of a square root is with a square root. So take the square root of the left-hand side, take the square root of the right-hand side. The square and the square root cancel. The only thing that's left over then is the x plus a 3. And then on the right-hand side, what we end up with is a positive and a negative. Now, notice how 54 is not a perfect square. This was Ahmed's question a minute ago. So unfortunately, these don't all end up with nice perfect squares. However, that can be simplified. So on the left-hand side, just leave the x plus 3 for a second. We're going to ignore that. On the right-hand side, we need to simplify root 54. So do that real quick. Those should be a couple easy numbers to come up with. There is a set of numbers that multiply to be 54, with one of them being a perfect square. All right, hopefully we get 9 and 6 correct. So left side, I'm just going to recopy it one more time. I get a positive and a negative 3 root 6. All right, so now the reason you kind of want to know both methods is because this second method is how I'm going to probably suggest that you write this. all right, when we just wrote it as the sum with a little plus minus in front. So if I now come to this problem here, I'm going to subtract 3 from both sides, subtract 3 from both sides. This will cancel. And what x would now equal is a positive and a negative 3 root 6. And then those are both decreased by 3. Now, since we're just kind of learning this, here's what this just means. I'm going to take a positive 3 root 6 and subtract 3. And I'm going to do a negative 3 root 6 and subtract the 3. So this expression here means the exact same thing as these two in blue. So if you wanted to write it as one answer, then you can write it in the yellow. That's totally fine. If you want to show that there's two completely separate answers, then you could take the yellow and break it down into the two blues. Since that's irrational, that's the first one that we have now is irrational with that root 6 here. You can't really do anything with it. I do not expect you, I really don't necessarily want you to most of the time to throw that into your calculator and give me a decimal. Okay, I want you to leave it as the exact answer with the root 6s in there. All right. All right. The next one I want to do actually as I look through these before we add too many layers too soon. Go to number 17. So now let's go to 17. In number 17, look at the 4, just to make this a little bit easier on us. Make that a 2. So just do this a regular squared. I am not going to make you do a 4th root power. So make that a squared. Do the first step that we talked about up here on the previous page. Isolate that squared term. So try to isolate that squared term in that problem. If I can get it back. And what I mean by that is, here's your squared term here. Try to get that by itself. See if we can do that. So what I have highlighted in yellow is kind of the variable that we're trying to eliminate. So we want to get rid of the 2. We want to get rid of that minus 5. All right, this is nothing more than if let me not do it in the blue. So if you look above the problem, if I just gave you this problem, 2x minus a 5 equals 157, that's one everybody can get right. You're doing the exact same steps in number 17 initially. So if I gave you this problem, I think most of us could look at that and say, yeah, if I'm going to solve that, I'm going to add 5 to both sides. So that's what we're going to do down here. You're going to add 5 to both sides. So those will cancel. We still have the 2. We still have x minus 4 squared. These would have canceled, and we now over here have 162. Now look what we have here. I'm still trying to get this by itself, so now I need to get rid of the 2 that's in front. So since the 2 is being... Was that Arba? Yeah. Oh, man. Time flies when you're having fun, I guess. What can I say? I thought we had a lot of time left. Okay, obviously no homework tonight, so you're spared finally without any homework. So bring this tomorrow. We'll pick up on this tomorrow, and then we'll see if we have enough time for homework after that. Okay? All right, we'll see you guys. Have a good day. I was thinking 53. I don't know why I was thinking 53. One class is 53. I don't know which one. All right. See you, girls. See you, Christian. Have a good day. I totally looked at that, too, and I was thinking 53 in my head.
I looked at it like 10:30 and I'm all curious about my past. And then I did look at the top again and so it's all right.
Yeah, I think that's why, because it was going by quickly. Like it didn't seem like it could be almost over.